Uh-oh.
Go ahead, Mike.
Oh, thank you. Sorry, I lost my screen there. Hello, everyone. Thank you for joining us for this installment of the Canadian Underground Infrastructure Innovation Center Academy Webinar Series. I'm Mike Kezdi, Managing Editor of Trenchless Technology Canada and Trenchless Technology Canada magazines. I'll be serving as the moderator today. Today's webinar focuses on the structural classifications of pressure pipe linings. Organized by the Canadian Underground Infrastructure Innovation Center, CUIIC, the University of Alberta, and Benjamin Media Inc., CUIIC Academy offers classes, courses, webinars, and events to help further underground infrastructure educational opportunities across Canada. The CUIIC Academy webinars happen on the third Thursday of the month, so be sure to join us on September 19th for our next installment, World Trenchless Day, Pipe Bursting Overview and Case History, presented by David O'Sullivan. For a full list of upcoming webinars, as well as past CUIIC Academy webinars, please visit academy.cuiic.ca. I also encourage you to save the date for the next in-person event hosted by CUIIC, the annual Pipeline Rehabilitation Academy, which takes place March 5th through the 6th in Mississauga, Ontario. More information will be available at academy.cuiic.ca. We'd like to take a moment and thank Westlake Pipe and Fittings for sponsoring the 2025 CUIIC Academy Webinar Series. Presenting today is Dave Kozman, Senior Product Engineer at HammerHead Trenchless. Dave has 30 years of related industry experience in pipeline manufacturing, design, construction, and trenchless pipeline renewal technologies for water and sewer applications. An ASCE Fellow and an ASCE Utility Engineering and Surveying Certification Board Certified Pipeline Engineer Water, Dave has authored and co-authored numerous papers, articles, and publications, helped develop and advance industry standards and specifications as an active member of various committees and associations, including ASCA, ASCE, ASTM, AWWA, CUIIC, ISO, NASCO, and NASTT. During this webinar, I encourage the audience to be interactive. By that, I mean, if you have any questions, type them into the designated panel on your screen. We'll try to answer as many of them as we can at the end of today's presentation. With that, I'll turn the webinar over to Dave.
Thank you, Mike. Appreciate it. So yeah, today I'm going to be talking about a wide range of different solutions and technologies that apply to pressure pipe rehabilitation and tie those to specific structural classifications, and as well as design methodologies, testing, and acceptance of those products and processes. And then lastly, touch on various industry standards in terms of the development and where we stand as far as progress goes. So from a pressure pipe rehabilitation perspective, there's various applications both in the municipal sector and private sector. Potable water applications, raw water, and sewer force mains are obviously very common to the municipal pipe networks. And when you talk about critical infrastructure in the industry, you may have various industrial applications as well as critical fire mains that are important to functionality of the operation. As far as different technologies that are available, the pipeline rehabilitation solutions actually date way back into the 1930s, with cement mortar lining first used, dating back to those early years. The first introduction of fully structural solutions date back to the 1940s with classical slip lining, which could be segmental lining or continuous. This involves pulling in or pushing in a diameter pipe that's smaller than the host pipe, and then usually grouting it in place after it's positioned. This obviously would include the reduction of a diameter, but is a fully structural standalone solution. A lot of these technologies actually started in the sewer sector and have evolved and developed into technologies that apply to certain pressure applications. Pipe bursting is shown here as first being commercialized in the 80s. There's different types of pipe bursting. There's static and pneumatic. It depends on the application, and it depends on the pipe material. It could be a size-on-size replacement, although it's categorized here as a rehabilitation technology because that's the way it's defined within AWWA standards. Or it could be a upsizing from let's say an 8-inch to a 10-inch or a 12-inch diameter pipe. And then cured in place pipe and close fit lining were introduced in the 80s and 90s. There's a wide range of different CIPP solutions in terms of the resin technologies and composite materials and textiles that are used, as well as the installation methods and curing processes. And close fit lining, essentially like a roll down process or a modified slip lining, where you will concentrically reduce the diameter of the pipe and pull it in place, and then basically re-round it out to meet the diameter or the inside diameter of the hose pipe, creating a friction fit. Polymeric linings were then rolled out in between the 80s and 2000s with in the 1980s, the epoxy type spray-on applications were introduced, as well as in the 2000s with the release of polyurea methods. And lastly, carbon fiber reinforced polymers, or CFRP technologies, were developed in the 90s. And these are typically man-entry solutions or applications. They can be installed either in a segmental fashion or continuous fashion. So as technologies are commercialized, typically they're rolled out to the general public and utilized for a number of years before the standards are developed behind that. And that's common to pretty much any industry. See that pretty widely in the sewer industry, and it's common as well to pressure pipe linings, meaning that in the 1980s, as mentioned previously, the pressure pipe rehab really took off. And with that, there was some industry development in terms of standards within ISO. And actually in the early 2000s, there was a push to develop definitions of various classifications of these lining systems, from a non-structural solution to a fully structural solution. And concurrently with that, within ISO and within AWWA, these definitions were published in ISO 11295, as well as closely behind that, the M28. These are loose definitions. They're qualitative in nature. The only difference between the two is that the way that they're classified, from Class A to Class D within ISO, with Class A being a fully structural solution, and Class B and Class C being hose pipe interactive, and a Class D system within the ISO definitions as a non-structural solution. On the flip side, AWWA classifies a non-structural solution as a Class 1, and then a Class 2 to Class 3 as a interactive, hose pipe interactive or semi-structural solution, and a Class 4 as fully structural. For those who have been involved in the lining business, either on a construction or a design side, or you would be familiar with ASTM F1216. It was first developed back in 1989, and it's the installation standard for CIPP that's installed using the inversion method. It's seen several iterations and updates. Here it actually says this was last updated in 2022, and actually within the last month, there is a new update in 2024, and actually does include updates to the pressure pipe equations. So look for that. That should be released here anytime. The this particular standard has some non-mandatory language in which covers the design aspects of linings, and it's been used pretty widely in the industry, regardless if it's CIPP or coatings or other different technologies. And there's some design checks specifically in there surrounding both gravity flow sewers and pressure pipe design, and it ties it to the condition of the host pipe. Many don't realize, though, that this standard was developed around unbonded, close-fit systems that are homogeneous materials. And the pressure pipe equations were actually designed or meant to be for low-pressure sewers, i.e. 10 psi and less. So if you look at that, you compare it to the AWWA Manual of Practice M28, in 2001, that's when these definitions or qualitative definitions were published in their non-mandatory appendix, basically giving you some guidance on what a Class 1, Class 2 to 3, and Class 4 systems should be. However, no design guidance is provided, and there's no correlation or tied to ASTM F1216, although they're often associated with each other. So with that, in 2013, in June of 2013, we were sitting in a committee meeting at AWWA, and the idea was presented to revisit the definitions within M28's appendices and expand upon them and develop a more concrete definition or definitions for that. So what initially was thought to be a fairly short putt ended up being a pretty robust project and turned into a comprehensive committee report. It's 40 pages long. It was developed through industry consensus, so all of the different technologies and products and classifications are included. It's available for free download on AWWA's website, so anybody can go and grab it. It includes, it not only addresses what the problems are, but ties it to the specific solutions and the tests that apply for both design and acceptance. And it also has some basic design guidance in the appendices. I'm going to cover that later because there's some other things going on in the industry today which are more applicable, but it is relevant. So the contents within this document are now being integrated into the new edition or release of M28, and that is near completion. It should be published within the next, hopefully, 6 months. And so what happened was the old edition of M28 had the non-mandatory appendix, which had all the definitions included. That is being eliminated and replaced with a standalone chapter, which includes the bulk of the content of the Structural Classifications Committee report. So it's become a permanent part of the document. It includes all of the different solutions and technologies, which we've already discussed. So this is something that it's taken directly out of that committee report. It's table 1. It shows you visually what each classification is meant to do, right? In terms of how it's defined, from Class 1 as an internal coating or non-structural solution, all the way over to a Class 4 fully structural solution. So as you move further to the right on this chart, you're picking up all the relative attributes for the previous classifications, okay? So as a Class 2 system, you're not only classified as a Class 1, but you also have the ability to span future holes in the pipe. As a Class 3 system, it can do everything a Class 1 and Class 2 can do, but also has resistance to external loads or negative pressures should the pipe go out of service or be decommissioned. And a Class 4 system does everything a Class 1 through Class 3 does, but is actually a fully structural standalone system. It's designed to take on all internal and external loads. So essentially there's sequential building blocks. I put this visual up just to show you what, basically from a bird's eye view, what different standards really accomplish from a design perspective. ASTM F1216, just like many of the design methodologies that are out there for pipe linings, it basically addresses design checks in the hoop direction or circumferential direction, which in most cases controls. But as you can see, when you're looking at different dynamics and different applications, you may have longitudinal forces, which you have to look at, and you should look at with each pressure pipe application. So those aren't addressed in F1216. The committee report checks more boxes. M28, as mentioned before, they provide qualitative definitions, but no design guidance. So there isn't any design procedures within M28. So I know this is hard to see visually, but essentially these came right out of the committee report. You determine what your design objectives are. In the process, once you determine those objectives and you understand the capabilities of a particular technology, you then select your technology, you align that with the appropriate tests for design, and then you determine what the acceptance tests are for validation of the installed product. So as you look at a project, you're defining what the problems are. You have to understand the type of material, the host pipe material that you're dealing with. When was it manufactured? What's the size of that pipe? What's the wall thickness currently? Is it deteriorating? Is it from the outside in? Are there major deficiencies in mechanisms that have to be addressed in advance, that the lining system has to accommodate? And what's it actually conveying? Is it drinking water? Is it sewage flow? Is it industrial flow? Is it seeing a wide range of temperature fluctuations? What's actually going on? From a loading perspective, there's internal loads and potentially external loads. External loads, for those who have designed gravity flow systems, obviously apply to all gravity systems. And that would include any hydrostatic loads, any surface loads, potentially any soil loads that may exist, and any special load cases such as ground movement or any type of special applications. In the case of pressure pipe, this would occur when the pipe is out of service or decommissioned. It's not going to always be there, but when it's out of service or decommissioned, it could see those loads in addition to a potential vacuum load. What we have to pay attention to here is, what are those loads? How often do they occur? And how long are they seeing those loads? We often see designs that are for 50-year service, for a 50-year external loading, for, thinking that pipe would actually see that over a 50-year duration, when in fact it may or may not ever be out of service. It may or may not ever see those loads at all. So as you continue on, if you see the pipe it's physically in service and actually under pressure, that internal load is going to offset the external pressure in most cases. So those static and potential surge or transient loads obviously have to make sure that you can accommodate, host pipe can accommodate the test pressures too during hydrostatic pressure testing after the pipe is lined. So these are different loading dynamics that you may see. There's also what we call functional requirements. Essentially, when the pipe is in service, there's just things that it needs to do to function properly as a pressure pipe. In the case of, for instance, a potable water line, you're going to see potentially a number of service connections if you're dealing with a distribution line. And how are you tying into those? Are you reinstating those robotically? Are you tying into those externally? And in the ends as well, you got to make sure that your end seals are attached properly and that you're getting a good tight fit. We call that hydrostatic integrity. Some call it water tightness. They're interchangeable, but essentially, you look at those things and they're critical to long-term performance of the system. And the ability, let's say you have external forces or you have some adjacent construction activity that maybe creates damage to a particular segment or area of a line pipe. How are you going to repair that? There's got to be a procedure for that. And if you have future connections, can you tap that? Can you tap your line pipe? And how do you do that? What are the methodologies that are available? The host pipe itself, if you anticipate that it could fail, what is that failure mechanism potentially? What are the dynamics behind that? Is it a brittle fracture? And if it does fracture and fail abruptly, how will that transfer to the liner? If the liner is in fact considered a Class IV system, or interactive for that matter, is that going to impact its ability to continue to function as a pressure pipe? These things have to be understood up front. And you align all the products with testing methodology. First of all, to really develop your basis of design. How are you designing your pipe, your lining system? Again, paying attention to the orientation of the testing in terms of your properties that you're achieving. Which orientation or direction are you testing in? You see visually here, the tests that are shown are in the hoop direction, which again predominantly drives your performance for most lining systems, particularly ones that are anisotropic, meaning they have variable properties in the hoop direction versus the axial direction. If you have a homogeneous system, you could test in either direction, and you should have inherently have the same mechanical properties. But what's important to note here, beyond just test orientation, it's having representative samples in terms of what's being installed. Is that a representative geometry of what you physically tested and base your design off of? Is this what you're expecting to see installed in the pipe? Because that affects your performance long term. And if you have situations that go beyond the norm, if you have anticipated conditions in the field, such as if you expect that the pipe could move axially or longitudinally, or if you have the need to tap the line pipe, and you want to take some of that pipe and you want to actually, from the job site, if you can, and perform what's called a demonstration test, and see how it will behave, and it will suffice or meet the requirements of the project. So once the liner is installed, regardless of what it is, it then has to be evaluated. Essentially, you're validating what's being installed. You're validating design. And so there's a lot of things you can do. First of all, the most important thing is your visual inspection of the ends, and physical inspection either inside through manual inspection if it's large enough, or through CCTV inspection. Looking for fit and finish. You're looking for making sure that with the geometry of the material and making sure that it's got the physical characteristics, visual characteristics that it's intended to have going into the design. Performing your hydrostatic testing, making sure that the pipe can hold pressure, and then capturing samples to perform mechanical properties testing. Again, this is to validate your design. Bacteriological testing is generally performed by the municipality, but of course that's key too before putting a pipe back into service. So you may have situations where, unfortunately these situations happen where what you put in the ground does not reflect your design. And why is this critical? Well, with pressure pipe, again, we're talking about something that's under pressure, internal pressure constantly. And so it's under constant tension. And so you have to make sure your composite system is intact or on the full circumference. And so if you have any anomalies, geometric features, or system imperfections that are shown here, those have to be reconciled. Essentially, you're going to capture samples of those representative samples of what's installed. You're going to do type testing to test for various mechanical properties, compare that to your basis of design, and then basically reverse engineer it to make sure that, or validate its performance. If it doesn't meet the physical requirements of the project, then potentially you have to go back and maybe look at doing some kind of corrective action. So with that, during COVID was good and bad. From a product development and specifications and industry standards development perspective, it was a very good thing because there was a lot of there was a lot of interaction, obviously a lot of virtual activity in developing standards. And from 2018 through 2022, there was a lot of key standards that were developed within AWWA. The CFRP industry developed a standard in 2018. There was a pipe or a polymeric lining standard that was developed in 2019, pipe bursting as well in 2019. And then CIPP was the most recent standard in 2022. What's important with that is that the C623 standard, there is activity, as I mentioned before, that's going on now within the industry in developing a design appendices, non-mandatory appendices, which is specific to CIPP, but many of those concepts will be transcribed onto other technologies such as SIPP. This is currently out for ballot. It's been ongoing collaboration with a industry committee to develop a design methodology for CIPP. So look for that. It's again initially out for ballot. We're hoping that we're going to get positive feedback on that, but a lot of really good things going on. And of course, M28 fourth edition will be out soon. I've also shown some ASME standards that are shown here that are very similar in terms of approach to pressure pipe design, that are applicable to non-metallic systems, thermoplastics and thermosets, and are really used more so in the power piping industry, but the concepts and design approach is very similar. So just a list of the different standards and things that have happened, in terms of all the activity over the recent years. There's a lot that's gone on. And this is all volunteer work within the industry, again, with the collaboration and industry consensus that's required to develop these standards. It's a big task, but I encourage you that don't have these standards or access to them to try to get a hold of them. But to start, again, one of the things that's important is that this structural classifications report, again, is for free. You can download it off AWWA's website, get familiar with it and the ideas and concepts behind it, because it's formed the backbone in terms of moving forward and helping to advance other standards and develop new ones. So that's where we're at in the industry today. And it's constantly evolving and changing, but we've made significant progress over the last 10 years, and we see a lot more to come in the future. So with that, open it up to questions.
Great. Thanks, Dave, for presenting today. As Dave mentioned, we're in the Q&A portion of today's webinar. So encourage everybody to enter their questions in the designated box. We'll try to get to as many of those as we can today. First of all, Dave, is there are there different materials for potable water applications versus sewer, and what governing bodies dictate this?
Good question. Yes, the answer to that is yes. First of all, in potable water applications, you need NSF certification, NSF 61 certification, right? And so that generally encompasses majority of those technologies are epoxy-based resins for instance, for CIPP. And then for other technologies, spray-on technologies, there are polyureas and of course epoxy spray-on technologies that are certified as well. So that's the first part of that. And then when you're dealing with sewers, particularly with force mains, they're actually, from a design perspective, are more rigorous than water mains, because they see a lot of cycles, a lot of cycling. So there's a need to make sure that you're utilizing a product that can withstand negative and positive pressures. And you've also got an environment, a sewer environment versus a drinking water environment. So for instance, if a reinforced material for a force main, generally you need to have a strain corrosion, data for reinforced composites. That's an important aspect. So there's different testing methods and different things that are required that are unique to those applications that are different than water mains.
Great. So generally speaking, when does it become less cost effective to line a potable water pipe rather than replace it? Is it a linear criteria? And we're also assuming that the external condition is not the driver to replace it.
Good question. So this is kind of a multi-tiered answer here, right? First of all, it has to do with the location. Obviously, if you've got a lot of utilities and would be cost prohibitive to really manage anything through those utilities if you have to dig around them or relocate them, et cetera. So anytime you can minimize disruption to those utilities by lining existing pipelines, that's a plus. Obviously, there's the scope of work as well. You know, the larger the project, the economies of scale will drive down pricing. Location of project, that's another thing that has to be looked at, because in the pressure pipe market, from an installation perspective and contractor network perspective, there aren't as many of those out there that are qualified or trained to install pressure pipe systems as there are, let's say, with gravity sewer main rehab. So you're going to get fewer bids, generally speaking, and which in some cases would actually eliminate lining because of the pricing. But if you do have, you know, a network of installers or contractors in a geographical area that encourages a good competitive bid, as well as have a scope of work which does the same, then that encourages obviously more competitive pricing. So we see that a lot where the scope may not be large enough to generate interest, and therefore either drives the price up or eliminates it completely. And that's something obviously we would like to try to improve on. Does that answer the question? I don't think I can hear you, Mike. You're muted.
How about now?
Yeah, there you go.
All right, sorry. All right. So will the additional chapter of the M28 manual include design formulas, or will the North American industry continue to use F1216 with the additional appendices for pressure pipe?
Good question. So the M28 4th edition will not include design procedures. However, it will be basically, I wouldn't say a regurgitation of the committee report, but a basically pulls in the most relevant aspects of that report and guides you in terms of, you know, testing and different methods that are recommended from a design perspective. ASTM F1216 has been utilized pretty widely in the industry, good or bad. It's served it well. There's a much more robust approach and more applicable approach that I think I mentioned before that is currently being developed and is out for ballot, and that's the design appendices to accommodate the C623 standard for CIPP within AWWA. It is a paradigm shift from anything I think the industry has seen, but it is in alignment with where the design should be from a practical perspective in terms of what the liner's seeing from a loading standpoint. So we hope that'll be finalized, although it's out for ballot. So that process does take some time to navigate and finalize. but the ultimate goal is to have that available to the general public within the next year. And to finish that up too, I mentioned as well, ASTM F1216 appendices, equations X1.5, X1.6, and X1.7 have changed. So everybody knows the new release of ASTM F1216 2024 edition should be on the streets. It should be available. Those three equations have changed, so everyone knows. And it's very slight modifications to it, but essentially we've corrected an error in one of the equations and have also corrected the approach to the others. Mike is still there.
All right, better. There we go.
Yeah.
I've read the CRF, so I don't know if you just answered part of this question in your last response, but we'll throw it out there. I've read the CRF for 50-year life provided in F1216 may not be conservative enough when extrapolating values at 10,000 hours. Do you have any comment on this? Also, how do CRF values for SIPP compare to CIPP?
Okay, so first of all, CRF stands for creep reduction factor, essentially. So essentially, what they're asked the question is they're relating it to F1216 not being conservative enough. Well, first of all, there isn't a value. ASTM F1216 states as a minimum. It, as an example, says it could be 50% retention of your initial properties long term, but that's not a hard number. It's just an example. It can be whatever it is. It could be 20% of your initial properties. It could be 80%. That number is what it is. For CIPP, it's going to vary on the product. It's going to vary on the composition of the material, the resin technology, the type of material. For this, in this case, for CIPP, it would be a reinforced liner. The type of composition. It's going to depend on a lot of things, but from our perspective, generally speaking, the value for CRF for tensile properties, again, there's tensile properties and there's flexural properties as well as compression properties that are covered by D2990, the creep testing. If you apply the applicable load or relevant pressure to that, the applied load of the specimen in tension, which has to reflect the in-service pressures of that pipe, you're looking at least 50%. We're seeing up towards a 60+% over a 10,000 hour period extrapolated out to 50 years. So, and from a CIPP perspective, we're seeing values in excess of 50%. For SIPP, I can't speak to that, but I can also tell you that composition also varies. There's varying types of different SIPP technologies, so that will vary.
Great. So how applicable will the new design procedure in the next revision of C623 be to SIPP?
Great question. So the SIPP committee is involved in the CIPP committee for development of the design appendices, and with the intentions of the SIPP design procedure to basically utilize the concepts, not all of them, because obviously it's a different product and process, but the basic concepts of design will be transcribed into the SIPP methodologies. That has not yet been developed or drafted because they're waiting for the CIPP methodology to be finalized and published. And once it is, then that will be transcribed, a good portion of it thereof, into the SIPP.
Are there any online calculators available in the industry to estimate CIPP liner design thickness?
There are, and the F1216 approach is very, very simplistic, and it's what we have to understand with pressure pipe lining systems is majority of them, at least on the class 4 side, are not homogeneous. They are reinforced materials and therefore are not based on wall thickness. They're based on hoop capacity, essentially. So it's not generally a minimum thickness. It is just the capacity of the material to withstand the pressures. And if it's a homogeneous system, like for instance, let's say like a solid wall polyethylene pipe, it is thickness based because it's the thickness drives basically the ability to withstand pressures. But for a reinforced composite system, it's not based on thickness. It's based on hoop capacity. But yes, there are calculators available. They're very simplistic when it comes to F1216, generally speaking. But once the design appendices becomes available and published for CIPP, it is a more robust design.
Right. So there's newer long-term physical property testing being done with 10 to 20-year results. How do you think these are considered, these should be considered today versus the previous results?
Great question. And yeah, I know that there's some samples that have been exhumed in various parts of the world. I think there was some that were exhumed up in the Toronto area and some overseas and other parts of the country here, and then compared to original values. A lot of the testing that I've seen, the values that I've seen have to do with flexural properties rather than tensile properties. And of course, both are important, flexural being important to withstand external loads and any longitudinal, potential longitudinal movement, et cetera. But, tensile properties are critical to the performance, for the most part, of a pressure pipe to withstand internal pressures and long-term performance. But from what I've seen, the exhumed samples over the course of, like you said, 10 to 20 years have been very encouraging, and in most cases are as good, if not better, than the originally installed product.
Great. Can you perhaps discuss some of the pros and cons for each liner, the classification, for each liner, common problems with each one, perhaps?
I can do my best, so there's obviously various levels in terms of structural capabilities and classifications. If you start with a class 1 system, you're looking at essentially like a cement mortar lining or like an epoxy type spray-on application. And it's really, essentially a corrosion barrier. It's not meant to provide any structural value, and it could be for, help for taste and odor, et cetera. But, generally speaking, those have to have a lot to do with surface prep. I know with CML, it doesn't generally bond, that well, but it doesn't really need to, because it does have some inherent stiffness to it. But spray-on systems obviously don't have as much of a, from a practical perspective and looking at, anomalies and what have you that affect its performance. They're not meant to be structural. They're meant to be barriers. But surface prep is critical. You have to make sure you have a good preparation of the surface, and so it gets a good bond, as good a bond as possible. So those are some challenges with the coatings. In terms of linings, there's a lot of different considerations. There's the layout of the project, the size of the pipe, if you've got bends, if you don't have bends, the level of pressures that are involved, the size of the material that's being involved. You want to make sure, I think I showed you some pictures on the design reconciliations piece. If you have a pipe liner that's oversized, that goes into a pipe and it creates, some anomalies that maybe weren't expected and weren't accounted for in testing, that affects performance. So there's aspects like that have to be looked at. There's a lot of different considerations, but a lot of it has to do with the basic principles of just getting the proper sizing, number one, and looking at the layout of the project and getting proper surface prep and installation procedures in place to get a repeatable process and consistent quality product.
Right. Now, you talked about testing of liners. Now, this is generally just a fraction of the cost of an overall project, but what is the importance of this, minimal investment in the overall performance of the system and future pressure pipe rehab work?
In terms of testing?
Yes.
Yeah. So this is something that comes up a lot. There's a lot of discussion on how frequent should you test? How frequently should you test? And in our opinion, it's best to test every segment that goes in if you can. And the reason for that is overall, these mechanical properties tests that are performed, generally speaking, let's say you do mechanical properties for, flexural and tensile, those tests are very affordable. We're talking just $200-300 a piece. And if you're talking $200-300 every time you install a liner, that's peace of mind, right? And so it's in terms of overall cost of a project, it pales in comparison to the ultimate risk of not doing it and making sure your checks and balances are in place. If you have a project where, let's say, you're doing a traditional sewer lining project, and generally the costs per foot are a lot less than they are with pressure pipe lining. From a percentage perspective overall, yeah, it's a little higher, but even in that case, it's a good idea. More testing is always good, right? Economically, it makes perfect sense, especially with pressure pipe.
Right. So how can people get involved in the AWWA committees, and I guess all of the committees that you referenced, to stay on top of the latest updates and contribute to the discussion?
They're always looking for volunteers, always looking for good insight, and so anyone that's interested, they can reach out to me directly, and I can get that off to the pipeline rehabilitation chair within AWWA, and then we can start that process. First of all, you do need to be a member, obviously, have to be a member. And then the committee chair would then reach out to you and then understand what you're looking for, and then, add you to committees.
Great. Well, that wraps things up. So thank you to everyone who asked questions today. And thank you again to Dave for taking the time to present today's webinar. On behalf of CUIIC, I'd like to thank all of the CUIIC members listed on this slide for their continued support in fostering underground infrastructure innovation and education across Canada. Finally, I'd like to thank everyone who attended today's webinar. We look forward to seeing you for our next webinar on September 19th. Thank you, everybody. Take care. Have a great day.